Okay. The next talk is Professor Xuefeng Liu. He is also the PR of this workshop from China side. His talk is an introduction to the modeling, measurement, and analysis of photon state spatial distribution in nanoscattering. Welcome, Professor Liu.
Thank you, Nanjing. Thanks to all people who both study in Glasgow and Nanjing. You're working very hard to get this conference goes on, and so far, as Nanjing has said, so far so good yesterday, and I said again today, so far so good. This is my topic. I'm Xuefeng Liu. My institute is NJUST. We have a research institute called RINRO, which do nano resolution imaging by indirect parameters. Tomorrow, Professor Xuefeng is going to give a more thorough introduction of this institute. So today I'm just point to you guys that yeah, this is the equipment we are working on. We are working on equipment, not we're working on imaging, of course, but the core work for us is working on equipment. So the purpose of the equipment is taking super resolutional images. Our purpose is slightly different from the previous presentation. May I stop for a while? Hello, Glasgow, can you hear me?
Yes, we can hear you.
Great, great. So our purpose is slightly different. It's like, yeah, we are trying to break in the limit. That's our job. We're breaking the limit in fewer ways. Way one is to really get the spatial limit. For example, the wavelengths, quarter of wavelengths. We need breaking this limit to something like 1/30th or even 1/50th of a wavelength. Or even we trying to sense something to 1 nano scale. Breaking the limit in the second way is that we not just measure 2D, not just the 3D, we measure multiple dimensional informations. Like yesterday, the guy was talking about the angles with us. We measuring the photon status, so we have a condition to get more information. And thirdly, we do chemical structure and chemical composition imaging. We do this imaging, of course, from the surface right to the depths of something like 50 millimeters. That's the target. But so far, we have certain difficulties. Yes, we are making systems, we are making equipment. So this slide, I'm trying to introduce that. A conventional microscopy, not confocal, not the Nobel Prize winning systems, not just 1 nanometer narrow field. We are talking about a few tens or even a few hundreds of microns in diameter. For this system, we need to do a lot of conditioning. We need to do uniformity of homogenization of the light source. We needed to prevent the thermal effect. We needed to reduce the other noise coming into our illumination. So we're using color illumination. We also need a good condenser to generate a bright pupil for the whole entrance pupil for the whole imaging systems. So come to now, I just introduced what we do in illumination. Of course, in the illumination side, we tuning the photon states. Yeah, upwards we come to the system. We need to look into the field, how much of the quantity of light that we're taking on and transported into the image plan. So this is at the objective plan. As you can see, we can do the Rayleigh unit. So we don't care about wavelengths, we don't care about the refractive index. We take this ratio as one Rayleigh unit. So along with, if we don't care about that, of course, you're using various kind of wavelengths, you use very kind of materials index. Then the depth here taken at right the middle of the field. So that the depth focus taken halfway is about from 8 to a sort of 24 Rayleigh unit. But in fact, in this a sort of 16 Rayleigh unit, we're only half of it, or even a quarter of it are really available for transport of real imaging from the objective plan, which is in here, to the image plan, which is in there, through the objectives, of course. So yeah, then the depth of focus is something you can express in somewhere here. The whole envelope of the depth of focus, as you can see, one of the students, Wei Liu, has done this survey. In 100 times objective, we have this Y width. It's about the envelope of that is determined by the width. The width is determined by the whole wide of the field, but the depth of it in this envelope is half of that is only 750 nanometer. So we only, at one time, we only transport this amount of light in this field to the image plan to overlap it on the sensor. So taking one example in the aluminum gallium arsenide with a variable chemical formulation with the X varies, then you change the nonlinearity. Say if the envelope of depth of focus is this large, if the X is 0 or X is 1, or X is 2 or something, and then you have a very low nonlinearity, you got a nice spot being transported from the objective plan, which is in somewhere here, to the image plan. And if you increase the nonlinearity, then you got a spot has a dipole. That the second harmonic generation produce a dipole moment that you can see already. There is dipole you can see in the image plan. So if you tightly focus the system from a certain 10 times, you change it to 100 times. The objectives, the objective NA, you change it to something 0.8, for something of 0.1. Then therefore, your focus is tight. In this case, your second harmonic generation is stronger. As you can see, you got no longer conventional spot. You got a smaller dipole in X and Y direction, and the Z component is projecting also in the XY plan has multiple features you can see. So yeah, so the whole microscopy is dependable. The photon generated in the objective plan transported into the image plan is dependent on the photon state itself. So that's the whole idea. We do PIMI, parametric interactive microscopic imaging. The PIMI measurement is depending on the photon states. Actually, you excited on object. Some case in the laser, rich laser, for example, you have a near field effect. although we have a mode, maybe a single mode being collected, being transmitted to the far field, but in the near field, you have many modes. Yeah. If I enlarge it, if I put my circle of confusion, the depth of focus in here, then no matter how is the laser mode will transport and destroy the whole pattern in here, and no matter the nonlinear effect or the other optical effect will destroy the pattern, actual field pattern in here. But the electronic state, the photon state distribution at this level, on this end phase, that will maintain, that will transport, and that will be conjugated onto the image plane at the sensor. And we will pick up the distribution at here, but maybe not the field. Maybe we got no imaging at all, but the purpose of us is to convolute this up, to resolve it up, how the photon state distribute along this range. Then as the recent development in weight measurement, for example, the photon, when you come into quantum, the photon is actually, the whole imaging is actually governed by the resolution, the spatial resolution, and the resolution of momentum. That then again is dependent on your optical quality of the whole system. When the light is transmitted through an object which has at the interface has an angle, and in this case, this angle has perturbated the photons, the whole photon space. It splits the photon into two parts. One part that you can collect it in as one spot. If you collect two parts at the same time, then you got two spots. So that's the the photon state splitting. The splitting is just caused by as this equation shows, two different Planck signs, two different photon states here, and then you got two spots. So our imaging process is to get the whole spots, whole states come out from the object. So here we have one particle space object. I excited the particle, then I got a lot of photon states distributed at the in the circle of confusion. And then if I excited the particle with a variety, a kind of light, as I said, the illumination, I can control my illumination with different photon states. So if I can just give a circular polarization representation, and the circular polarization is weak, or I give a circular resolution photons, but the circular photons, the vertex is angled, it's not parallel to the optical axis, and then I got a helix sort of excitation, etc., etc. And if I got all this combined excitations, all go on this nanoparticle, and as you can see, you got a distribution, spatial distribution of photons being excited. As you can see on this direction, the photon states forms a dipole, and this direction, two directions, and you see another dipole. The photon states density concentrated in here are totally different from the density of state in here, and as it propagates, you generate other state, but you maintain this dipole state. That's what we opt. That's what we try to project on to the image plane. So conventional microscopy use, say for example, in the confocal system, you follow the Photon spec function. This is the Photon spec function field. You measure a labeled giant macro biomolecules. You tag it maybe that is a molecular model in MOVES. So you follow the point spec function tape. You can come to follow the molecular model move along the vein or move along another chain tissue. So that you can follow it up and see if it carries a protein of the virus. And then you can see how the virus come in, transmitted into, you can generate the channel of biomolecular, visualize biomolecular process. The resolution of this, this point spec function, it comes to 1 nanometer, as you can see. So yeah, but this is suffers a lot of actual environment problems. There's a lot of scatterings, as you can look. So come to this resolution is very rare. This is just for publication, but there's no such instrument actually on the market. You can really use it. It's good. So you can follow the rotor machine of the biomolecules. But no, there's no such 1 nanometer resolvable machine. But maybe in the future we can work on it. We can, as I said, our measurement methods are not suffering that much, but the noise, the scattering from the environment in the cell. There's also suffers very little of the fluorescent poisoning, all the other things. But the only thing we can reach that is that we can proper into this single point function point by taking all the photon states out from it and then projecting into the sensor. So that this is what we do, and this is what we achieve.
Professor Liu, another 2 minutes.
Oh, okay. I got that. Yes, this is what we got from BGI. This array of nano DNA spots. Each of them is 200 nanometer. Yes, I need to carry on this. We are developing the idea, trying to use Barry phase. Barry phase is generally a geometrical phase, as what we just talking about. We need the geometry. And also, Barry phase is tightly related to the integration, in the whole circle in the Poncast sphere. In our measurement, we're using dielectric particles. Here is polystyrene. This is the supplier give us SEM imaging. Some of them come to multiple microns. Some of them is a few hundred nanometer. The smallest nanoparticle we got is 80 nanometer. This is the measurement system. This is how we tap it into and how we integrate it, and how we image it and present it out. And this is the simulation we got for a 530 nanometer at 1 wavelength size nanoparticle. We projected the measurement along the center to the edge, and then cross the edge to the outer scattering, and then we're projecting into Poncast sphere. We got this line for the outer scattering, and this is for the inner scattering, and this is for the border. The center of the border is at this pixel point. So this is how we do it. And this is the real measurement. We also do the same thing. We got the outer scattering of the pixels. We got the inner scattering, and we got the border position, which is somewhere here. And again, we have a smaller one, as I just mentioned, 80 nanometer. In this case, the coupling is very weak. We don't see the helix whirling pattern. Instead, we just see the dipole here, and magnetic and electric and magnetic. So here is the 5 micron, 10 times of the wavelength. And then we see multiple kind of yeah. Well, this is 5,000 days. Same wavelength. Then we see a multiple mode being excited. There is an inner mode, there's an inner border mode, and there's an outer border mode, and the outer scattering mode. We excite three from there, four modes from 0 to 1 to 2 and to 3. All this mode produce a different kind of projection in the Phuket, and of course we image it in that way, and then we using AI, using a lot of other means to image, calculate the shape and the inner structure of this. In conclusion, well, in this measurement, we measured the things much smaller than the different mode. Differentiation limit is something. A quarter wavelength is about 250 nanometer. Something is about the differentiation limit, and something much larger than the differentiation limit. So across all the range, we can do the real beam imaging. So in conclusion, yes, we can overlap and do the simulation, overlap the X and Y component of the vector field for the simulation. I think we are all our precision optical wide field system can actually conjugate the electronic the photon states in the objective plane to the image plane. And certainly we can have a barrier phase concept to further carry it on to multi-mode of projection of the imaging. Within one mode, we are able also to analyze each individual mode and then see the variation of the photos, and then we can to promote the resolution from the direct limit 250 to something of 10 nanometer. That's we already realized. Thank you. That's all.
Oh, thank you for great talk. We have one question to ask. So, Professor Liu, at the moment, your PMI system, you can reduce the noise. We use the software to, for example, AI method to reduce the source. If have any, you use the hardware to reduce noise.
Yes, the hardware is actually in two parts or three parts. Say I just introduced the innovation part, and also, of course, there's also the light analytical part, and of course, there's a part that is the sample and substrate itself. Yes, then we are collaborate with Glasgow University. We are doing a lot of effort in the sample substrate part. Recently, we do plasmatic nano array structures. We're trying to do the perturbation structures to intensify, at each individual mode, the signal collection. So that's the major effort we're doing right now. Because the collection part and the illumination part, that we have already had a long history of doing that. We have, of course, we're doing more that is following the modeling programs. We use FDTD to indicate a particular sample for different protein or a different symmetry of the nanoparticles. We need to select a different modulation, select a different change in track in the punctate sphere. For example, in this diagram, for a circular polarized circular symmetry, we need to actually to do a lot of modulation around here, and of course around here. and also across from here to here. So the modulation, the field illumination change, taking multiple form. So that's on the equipment side. But yes, as you know, Glasgow has done taken the role in done a lot of new design. We are really looking forward to the new the nano array systems with code or without code, with plasmonic or with dielectric, with something else to come in. We will continue our research. Yes, thank you.
Okay, thank you again. And today we are finished. See you tomorrow.
Okay, that's all. Thank you.